Okay, guys, let's look at the first warm-up problem here. I have cosine 4x. The first question is, do I have any odd exponents? Do I have any odd exponents? Okay, this is for cosine sine problems. And no, I don't have any odd exponents, okay? So I'm not going to use the Pythagorean identity for cosine squared sine x, sine squared x, all right? If I had an odd exponent, then I would either save a cosine and change everything to sine, everything else to sine, or I would save one sine and change everything else to cosine, all right? But since I don't have odd exponents, everything here is even, then what I'm going to have to do is I'm going to have to use my trig identity, which I know cosine squared x is equal to 1 plus cosine 2x over 2, and if I need sine, it'd be sine squared x is equal to 1 minus cosine 2x over 2. And so how do I replace this with this? Well, I need cosine squared x, and cosine 4x is actually just made of 2 cosine squared x's, right? So what I have here is 1 plus cosine 2x over 2 times 1 plus cosine 2x over 2 dx. What I would do next is I would take out the scalar, which is 1/4, and then what I have left actually here is a plus b times a plus b. Okay, so what I'll have is 1/4 times the integral of, and this will be a FOIL with a middle child, so that's going to be 1 plus 2 cosine 2x plus cosine squared 2x dx. All right, and what I do is I want to get this where I have buy one, get as many free as I can, and I want to make sure that I can integrate each one of these. All right, and if there's any distributing that I can do for left, I need to do all the distributing that I can do. And so I've already FOILed this or distributed it. And is there any other distribution I can do here? No, this is pretty much it. But I do see that I have a 2 up here, okay, a squared up here. I can integrate 1, no problem. I can integrate, cosine u, no problem. But I don't know how to integrate cosine squared, or do I? Well, to do that, what I'd have to do is, once again, use my trig identity, okay? Okay, at this point here, I have 1/4 times 1 plus 2 cosine 2x plus this right here, using the formula that I know here, cosine squared 2x is actually equal to 1 plus cosine 4x all over 2 dx. All right, where did that come from? Because this x is a 2x, so this is going to be 2x, so this will be 2x, and that's why this becomes a 4x. Once I'm here, I can split this up into two fractions. So what I get is 1/4 times the integral of 1 plus the integral of cosine 2x plus the integral of 1/2 plus the integral of cosine 4x over 2. And I think I can take the integral here. This integral here is going to be, let me see, actually let me combine the 1 and the 1/2. So this will be 3/2 plus 2 cosine 2x plus 1/2 times cosine 4x dx. So now let me go ahead and take the integral. The integral of 3/2 is 3/2 x plus 2 times, so this 2 right here is just a scalar, 2 times the integral of cosine 2x. The integral of cosine 2x is sine 2x divided by 2, and the x's cancel out, so there's not a problem there. I also have this 1/2 here, which is basically a scalar. This would be times, plus 1/2. And the integral of cosine 4x is actually sine 4x divided by 4. Right, all of this is in parentheses because it's the integral of all of this times 1/4. All right, and then I just need to add Charlie at the end. This is basically my answer. I can simplify a little bit by saying 2 divided by 2 is 1. And 2 times 4 is 8. So this will be 3 halves x plus sine 2x plus sine 4x over 8 plus c. It can be overwhelming, okay? And so what you always want to try is use substitution first, okay? And after you do so many of these use substitution things, you kind of get the feeling that the derivative of x squared is 2x. And does your x cancel out here? No, you start getting the feeling that, hey, the derivative of this has an x in it, and you got to get that x to cancel out, and it's not going to cancel out with this 2. Had this been a 2x, this would have been an easy use substitution problem. Okay, so it's not an easy use substitution problem. This u being x squared plus 1 didn't work out for me. Okay, so what kind of problem is this? What other alternatives do I have? Arctan, okay? And the nice thing about arctan is it changes this u from x squared into an x. Okay, what do I mean? Because this is actually u squared. This will actually be a squared. So a squared equals 1, u squared equals x squared. So that turns the u into an x, which changes the du dx into 1. And so dx is going to be equal to du. Okay. So on this side, my a is going to be 1. Okay, I substitute 2 things. I substitute my u, which is this x squared, and I substitute my dx. It's the same. It really is just u substitution. Okay. The tricky thing, though, is now instead of substituting u, you substitute u squared. Okay. You're just trying to change everything into u's. All right. And then I ask myself the question, do my x's cancel out? Do they? Yes, if they do, then this is an arctan problem. Okay. On the other way, I tried the u sub. The x's didn't cancel out, so it wasn't an easy u sub problem. Okay. All right. So I've got this. It is an arctan problem. So I go look at my pink sheet, and it should look just like the arctan formula on my pink sheet. The du over u squared plus 1. What's extra here? The 2. So what I do is I pull out the 2. Okay, and I see that what I have left looks just like my pink sheet. So that means this answer is 1 over a arctangent u over a plus c. Okay, and the truth is, if you put that on your test and you have u defined somewhere and you have a defined somewhere, I actually would say you're almost there, right? It's a great answer. It's just the wrong answer, but you're pretty close, right? All you have to do now is put your a in and put your u in. Does that make sense? And I'm done. Okay? So the answer is 2 arctangent x plus c. Okay? Any questions on this problem? X is dx. Okay. I look at this problem, and if this were my u, the derivative of this doesn't cancel out. Okay, so it's not a regular u substitution problem. Okay, so what I'm going to do is I'm going to say, well, this is a p and this is a t, so it's a PT problem. You guys ready? Okay, so PT problems means I can use the table trick. Guys, what 2 problems can I use the table trick on? PT and PE. Okay, PT and PE. All right, so I'm going to take the derivative all the way down until you get 0. Since it's a polynomial, you will always get 0 at some point. All right. On this side, I take the antiderivative. So let's take the antiderivative of sine 3x. That's going to be cosine 3x divided by 3. Do my x's cancel out? Yes, they do. So that would be divided by 3. Then I do it again. Wait. I think this is a negative, right? The integral of sine is negative cosine. And then the integral of cosine is just sine. So this would be sine 3x over 9. And I'm trying to match this up. So this will match with the 2. And with the 0, this will be take the integral again. The integral of sine is negative cosine. So I'll have a positive here, cosine 3x divided by 3, which will be 27. It's with me on the integral side. Okay. Then I'm going to put a plus, minus, line. So my answer is negative x squared cosine 3x over 3 plus 2x sine 3x over 9 plus 2 cosine 3x over 27. And don't forget Charlie. Are there limits I need to put in to this? No. Okay. Any questions on this problem? Hopefully that's right. Someone give me a check on that. Is that right? Okay. All right, let's look at number, did we say 9? What number did we want besides that? Besides 3? Number 9. Okay. Let's look at 9. E2x sine x. Are there limits on this problem? Okay. All right. So if I were doing this problem, oh, I can see that it's an ET problem. You guys good with that? Okay. So ET needs to go home. Okay, so I know this is a UV minus VD. And my E is going to be U equals E to the 2x. I mean, my U is going to be E to the 2x. My dV is going to be sine x dx. The derivative of U is going to be 2E2x dx. The integral of sine x is negative cosine x, right? Okay, so this is going to be equal to U times V. So U times V is negative E to the 2x cosine x minus V times du. That's negative 2E2x cosine x dx. All right, the negatives get a little bit confusing, but you just carry it through. All right, this is a negative negative, so I know that's a positive. And so what I do is this right here has its own u dv problem, uv minus v du. So this is equal to negative e 2x cosine x minus, plus this its own uv minus v du inside here. Okay, so let's get this new uv v du thing. Okay, so I'm going to go over here. My u is going to be equal to 2e2x. My dv is going to be equal to cosine x dx. Okay, on the left side you take the derivative. The derivative of 2e2x is what? 4? 4e2x dx. The integral of cosine x is positive sine x. All right, and then I just put that into this bracket. So u times v is 2e2x sine x minus the integral of v times du, which is 4e2x sine x dx. All right. So what I have is an ET problem, which means I know ET needs to go home. Okay, that was the whole goal of the movie, right? Okay, so I'm going to recopy what I have. I have the integral of e2x sine x dx is equal to negative e2x cosine x plus 2e2x sine x minus, I'm going to take the 4 out, minus 4 integral of e2x sine x dx. And when ET goes home, from here on out, it's no longer a calculus problem, okay? What I'm going to do is, my goal is to solve for the integral of e2x sine x, okay? And I can use this algebra equation and solve. What I do is add 4 to both sides. So this is going to be 5 integral of e2x sine x dx is equal to negative e2x cosine x plus 2e2x sine x. Okay, you're going to add 5 integral of e2x sine x to both sides. And basically, my goal was to solve for this. So what I'm going to do is divide both sides by 5. Don't forget Charlie. And there's my answer. Okay, ET problem, guys. Definitely on the test. All right. Okay, I'm going to move on, guys. Tomorrow, I'm going to be here after school today, so if you need help after school, come hang out with me. All right, let's look at what we're doing today. If you look at your notes, okay, we're going to do tangent secant problems today, okay? And yesterday what we said was when we took the derivative of cosine u, okay, that derivative is sine u du dx, okay? So what we did was we saved, if we saved a sign, okay, then you change everything else to a cosine. And that's a strategy because the derivative of cosine is sine, okay? And you could do the opposite too, and we did the opposite too. We said, you know the derivative of sine u. Wait, did I do that wrong? That's a negative. Sorry, that's a negative, okay? We know the derivative of sine u is cosine u, okay? So we said, another strategy is if you save a cosine u, you can change all else to a sine u, okay? And it's going to work out, Okay, so we're going to do the same thing today with tangent secants. Okay, so tangent secants work like this. Okay, if you have the derivative of tan u, okay, what is that? Isn't that secant squared u du dx? So one strategy we could take is we keep or we save the secant squared u, and saving it means pull it to the side and don't combine it with anything. Like if you have another secant u, don't combine it with the secant u. Always like keep it pristine, the secant 2 by itself. Okay. If we save a secant squared, then all we do is change all else to tangent u, and things are going to work out. Why? Because the derivative of tangent is secant. Okay. But another derivative that we know is the derivative of secant u. Okay, and what's the derivative of secant u? Secant u tangent u. Okay, and what that means is another strategy that we could have is actually we save the secant u tangent u and we change all else to secant u. Okay, and things are going to work out. The integration is going to work out. Why? Because the derivative of secant u is secant u tangent u. Okay, and we're actually setting us up for success. That's really what we're doing. Okay, when we do this change, okay, we use this Pythagorean theorem, which is I tan in a second. Okay, so you use this formula to change it. Just like we did cosine, we used the cost of sin is $1, right? We use that one, okay? So let's go ahead and do our first problem and see how this works out. So our first problem is we have 5 tans, and we have 1 secant, okay? And for these problems, our strategy is we're either going to save a secant squared or we're going to save a secant tangent. You can decide what you want to save. Sometimes only one works, and sometimes both of them work, okay? So let's look at this problem. Do you want to save a secant squared, or do you want to save a secant tangent? What do you want to save? Secant tangent. Guys, do you see you couldn't save a secant squared? Like, that's not possible. There's only one secant, so you can't save it, okay? Unless, like, you go to the bank and get another secant squared. You get another secant, but no banks in calculus. Okay, so guys, this is what I'm going to do. If I save a secant tangent, then what I have is I have a tangent 4 left, right? Secant x, tangent x, dx. Right? If I save a secant tangent, then I have to pull one of the tangents out of this 5. And so all I have is 4 left. So everybody good so far? Okay, and I'm going to put save there. What save means is that I always carry it. Don't break it up. Don't remultiply with anything. I'm just going to save it. I'll just carry it wherever it needs to go. All right? So then the goal is, remember, let's look at this goal. If I save a secant tangent, what do I have to change everything to? Everything else to? Secants. So I save this. I change all of this to secants. Now, how do I change a tangent to a secant? Or how do I change 4 tangents to a secant? 2 tangents. Do you see that? I have to change it to 2 tangents. So this right here is going to be tangent squared x times tangent squared x times secant x tangent x dx. Remember, I'm going to save this, so I'm not going to change this one up. Okay, all of these need to be changed into secants. Okay, I'm going to use Pythagorean theorem. So this is going to be tangent is equal to secant squared x minus 1. Secant squared x minus 1, and then I still have this secant x tangent x dx. And I have to save this, so I'm going to keep it over here saved. Okay, so let's see if I've done what I needed to do. Okay, I changed it to, I saved a secant tangent, and I changed everything else to secant. Did I do that? Okay, once you do that, what you want to do is get by 1, get as many free as you can, meaning just get plus and minus signs. Okay, so the only way to do that is to distribute until you cannot distribute anymore. Okay, so let's look at what we have here. Can I still distribute? Can I distribute? Do you see a way that I can distribute things? Yes, okay. And what you guys have to keep in mind, and what students have trouble with, is they try to distribute everything at one time. That is absolutely impossible. Okay, when you distribute, you can only use like 2 factors at a time. Does that make sense? 2 groups at a time to distribute. Okay, there's no way. I have 3 groups here, There's no way I can distribute all of them at one time, okay? So let's just distribute the first part, these two factors first, okay? This is going to be a minus b times a minus b, okay? So not a difference of two squares. It's going to be a FOIL problem here. So this is going to be secant 4x minus 2 secant squared x plus 1, okay? And once you FOIL this, okay, this becomes a family. Okay, this becomes a family, and the algebra is where students have trouble here. This becomes a family, and the whole family gets multiplied by secant x tangent x. Okay, so I need you to look back up here, and I need to ask you, can you distribute any more? Is there any more that I can do to distribute? Yes, if there is, then you do it. You got to distribute until you cannot distribute anymore. Okay, and I can actually go backwards here, and I can distribute this secant tangent. Okay, so what I get when I distribute the secant tangent is, remember, this secant x needs to be saved. So don't combine the secant x and the secant 4x. If you do, it's not going to work out for you. Okay, so all I'm going to do is this secant x4, I'm going to keep it. Okay, this secant x tangent x, I'm going to keep that also. And I'm just going to set it right next to this. Okay, that's the first term right there. Okay, the second term, I'm going to multiply this by the second term. It'll be minus 2 secant x. Now there's two secant x's. And I'm going to multiply that by secant x tangent x. And don't combine these two secants. Okay, it'll give you problems if you do. All right, the whole thing was saving the secant tangent. Okay, and then finally, the last term, when I multiply secant x tangent x by 1, I just get, again, secant x tangent x dx. So all of this is getting integrated. Okay, so I thought I got to do one problem, but oh boy, I get to do three. That's so much fun. Can't wait. Okay, so what I want to do is ask myself, is there any more distribution that I can do? No. Okay, I mean, you could like FOIL this out, but don't do that. Okay, don't do that. Okay, and the reason is this. If I make this my u, okay, remember there's three different integrations here. If I make this my u, this means that is the exponent I will work with, okay? You add 1, divide by the new exponent. Don't forget to divide by the derivative of secant x. What's the derivative of secant x? Secant x tangent x. Do my x's cancel out? Well, by golly gee, okay? And that's why you leave the secant x tangent x, because you know the derivative of secant x is secant x tangent x, and that's going to cancel out. So for your first term here, your answer is secant x to the 5th power over 5. Okay, do you see what we're doing? So let's go to the second term. The second term, there's my u, secant x. Okay, I have a power of 2. I'm going to add 1 to the exponent, divide by 3. Don't forget to divide by the derivative of my u. What's the derivative of secant x? Secant x tangent x. Do my x's cancel out? Well, by golly gee whiz. Okay, so what I get here is minus 2/3 secant x raised to the 3. Okay, and finally, guys, this right here is not a u substitution problem. You guys see it? It's just on your pink sheet. So what's the integral of secant x tangent x? It's just secant x. Okay, and there is my solution. Okay, do you guys see the logic that we went through to do this? I mean, you want to save a secant tangent because the derivative of secant is secant tangent. Okay, all right, let's do another problem. Let's do your second one here. And your second one is the integral of tangent 4 3x times secant squared 3x dx. Okay, so remember we have two strategies, okay? The derivative of tangent u is equal to secant squared u du dx, okay? So we can save a secant squared and change everything to tangents, okay? Or, okay, the second strategy, the derivative of secant u is secant u tangent u du dx, okay? You can save a tangent u, you can save a secant tangent and change everything to secant u. That's our strategy, okay? That's your only strategy, okay? And that's actually what we've been doing for these secant problems. You just didn't know, okay? So let's look at this. Now you can choose. Do you want to save a secant squared, or do you want to save a secant tangent? Okay, let's save a secant squared. I think that's going to be easiest here. Okay, so what I'm going to do is I'm going to save a secant squared. Okay, good. This is already secant squared, so I'm going to save that. Okay, so if you save a secant squared, let's look at our strategy. If we save a secant squared, then we need to change everything else to tangent using this formula. 1 plus tangent squared x equals secant squared x. And I guess in this situation, it'd be 3x. Okay, so I'm going to change everything to tangent using this formula. Okay, do I need to change everything to tangent? No, everything's already done. Does that make sense? It's already changed to tangent, so I'm good. Okay, the next thing I do is I try to get a buy one, get as many free as I can. Okay, what that means is I distribute as much as I can. Okay, do I need to distribute here? No, don't distribute. I mean, that's it. Okay, so what we're going to do is we're going to rewrite this as tangent 3x raised to the fourth, because that helps me to take the integral. Okay, secant squared 3x dx. This is the same problem. Okay, so then if you've distributed as much as you can distribute, what you do is you find your u. There's my u, tangent 3x. Okay, if that's my u, okay, so guys, always, this will be your derivative. This will be your u. Okay, that's why you change everything to tan u's, because that's going to be your u's. Okay, you're going to take the exponent, you're going to add 1, divide by 5. Don't forget to divide by the derivative of your u. Guys, what's the derivative of tan u? What is it? Secant squared u times du dx. So the derivative of tan u is secant squared u times what? Times 3. You guys good with that? Okay, so let's make sure we walk backwards correctly, okay? First, you add 1 to the exponent, then you divide by the new exponent, okay? Then you divide by the derivative of your u, okay? Then you have to check, notwithstanding your u's, do your x's cancel out? Did they cancel out? Yes, so my answer is 1 over 15 tangent 3x raised to the 5th power plus Charlie. Can you guys do that on your own? I feel like this type of problem you've seen before, right? If you have a question? It is. It's a regular U substitution, yes. And you did this before. We just didn't talk about it in this shortcut way, kind of. Okay. Let's go to cosecant cotangent. All right. The cosecant cotangent works the same way. Students are intimidated by it, but really it's the same thing with a negative. Okay, what's the derivative of cotangent? Negative cosecant squared du dx, right? So the strategy is, if you save a cosecant, okay, save a cosecant squared, then you change all to cotangent u, okay? The other formula we have is the derivative of cosecant u. And what's the derivative of cosecant u? Negative cosecant u, cotangent u, du dx. Okay, same strategy. If you save a cosecant u, cotangent u, then you change all to cosecant u. Okay, and the way you change it is a Pythagorean identity. So this Pythagorean identity is I cut. This is just x. So x equals cosecant squared. Okay, so let's go ahead and do this problem. So this problem is cosecant 4x cotangent 4x dx. Now you tell me, would you rather save a cosecant squared or would you rather save a cosecant cotangent? Look at the problem. Yeah, I think the cosecant squared might be a little bit easier to save, but you could try the other way and see if it works, okay? So I'm going to save a cosecant squared x, okay? So that means I'm going to save that. So what I have left over is cosecant squared x times cotangent 4x dx. We're good with that. So I'm saving it, okay? What does save mean? It means don't remultiply it with anything, okay? Save it. All right. Then if I decided to save a secant squared x, that means I have to change everything else to what? Cotangent. Is it all changed already? No. This one's not. So I'm going to change this to cotangent. And to change cosecant squared to cotangent, that's 1 plus cotangent squared x, okay? That's using the Pythagorean theorem. Okay, so that's what I do. I save a cosecant squared. I change everything else to cotangent. okay? Then I want to get, by 1, get as many free as I can. And the way to do that is actually to just distribute until you can't distribute anymore. Okay, so let's go ahead and distribute. What do you want to distribute first? You want to just take these two first? Does that make sense, this one and this one? Okay, so what I'm going to do is distribute this cosecant into this parentheses. And again, guys, where students mess up here is they try to do like everything at one time, okay? Just take it one at a time. So this is going to be, save a cosecant squared, okay? And when I multiply, I just get cosecant squared. And then I'm going to add it. I'm going to add it with cosecant squared x times cotangent squared x, okay? Once you distribute this, okay, this becomes a family. Okay, students have trouble with this algebra. This becomes a family, and we still have a cotangent 4x out here. We have a cotangent 4x. Okay, so now I ask myself the question, have I distributed all that I can? No. Do you see I can do this backwards distribution like this? Okay, so let's go ahead and do it. And when I do it, I still want to save a cosecant squared because that's what I decided. So I'm going to save a cosecant squared. That's going to be cosecant squared times cotangent x raised to the 4th. Okay, I also have a cosecant squared here times, what's cotangent squared times cotangent 4? Yeah, cotangent 6, right? So I'm going to have cotangent x6. And I think that's it when I distribute. I still have just a buy one, get one free. I was hoping for more free, but not bad. Okay, one free is better than none free. It's still like 50% savings, right? Okay, so here I am, and here's the question. At this point, I should be, if I save the cosecant squared and change everything to cotangent, I should be able to solve each one of these individually. Let's see if we can. All right, this would be my u. Add 1, divide by 5. What's the derivative of cotangent x? Negative cosecant squared x. Do my x's cancel out? Notwithstanding your u, do your x's cancel out? Why, yes, they do. So this becomes negative cotangent x raised to the 5th power over 5. Okay, let's look at this term right here. Okay, this will be my u, this cotangent x. Okay, add 1, divide by 7. Don't forget to divide by the derivative of cotangent x. What's the derivative of cotangent x? Negative cosecant squared x. Do my x's cancel out? Yes, so this becomes negative cotangent x raised to the 7th power over 7. And don't forget Charlie. Feel like you could do this on your own?